Hello everyone, I am Devanjan Chakraborty, a student of third year from Kujbehar Government Engineering College in EC department. Today I am here to discuss PCM, that is Pulse Code Modulation, a topic from digital communication and stochastic process. Let's start with the intro. Pulse code modulation, commonly called PCM, is a technique used to represent analog signals such as speech, music, or sensor outputs. Instead of sending continuous analog signals, PCM samples of the waveform directly send at regular intervals, which then converted into numerical value and then express that value in binary form, zeros and ones. This approach was first developed by Alec Reeves in 1937 and was initially used in military an early telecommunication system. Today, PCM is present in almost every form of digital media, from telephone networks to music CDs and internet video calls. Let's discuss the key idea of this PCM. The key idea of converting continuous time continuous varying signal into a digital sequence that it can be easily stored in memory devices. It processed using computers or digital signal processors. It's transmitted over long distances without significant degradation from noise. And, and its advantages are high noise immunity, easy to process, it's safer and compatible with digital switching and networking. Let's see the block diagram of PCM. Here we can see the analog message signal passes through the low pass filter following sampling quantization through the binary encoder and goes through channel decoder, and at last we get the reconstructed signal. There are three fundamental steps in PCM. They are sampling, quantization and encoding. Let's discuss this. Let's discuss why do we need these fundamental steps. Here we see a graph. Here we see a signal graph with continuous amplitude. So can we calculate how many amplitudes are there? There are infinite numbers of amplitudes since it's continuous in amplitude. Can we calculate it? What intervals is the amplitude of the signal is defined? There is no such time interval where the amplitude of signal is defined since time is continuous. It's due to this reason we have to convert continuous time continuous amplitude to discrete time discrete amplitude. Now let's discuss sampling. Here we see a continuous amplitude signal. Through sampling we get an output signal which is only available in integer multiple of t's. Since t's is constant, so the time axis of discrete time has variable n. What's quantization? To, disc- to discrete the amplitude, we use quantizer. But why do we use quantizer? Here we see a signal. This signal is going towards infinity, but the amplitude of signal is still continuous even after taking amplitude at distant time intervals. Hence, we use quantizer, which maps each sample to nearest available levels. The more is the quantization level, more is the accuracy of the signal. Quantizer are broadly classified in two types: uniform quantizer and non-uniform quantizer. What is encoder? Encoder is a block that converts the quantized values into a binary code for digital transmission or storage. Each quantized level is assigned a unique binary number which represents the amplitude level. Here is the block diagram of encoder. If a quantizer has 4 levels, encoder needs 2 bits for each level. If a quantizer has 10 levels, encoder needs 4 bits for each level. If a quantizer has 1000 levels, encoder needs 10 bits for each levels. Now let's discuss another important topic, that is signal to quantization noise ratio, SQNR. The signal to quantization noise ratio of the quantizer is defined as S by N, that is signal power normalized by noise power normalized. The noise power is given as noise power equals to V square noise by R. Since noise is defined by random variable eta and PDF if eta, that is the mean square value of eta, that is noise cancellation error. Here we get the expression. Now when the load resistance R equals to 1 ohm, then the noise power is normalized, that is noise power is equals to V square by noise is by 1 equals to del square by 12. The number of bits v and quantization levels q are related as q is equals to 2 to the power v and del equals to 2x max by q is equals to 2x max by 2 to the power v. Sq is equals to rho by del square by 12 equals to 3 square max equals to 2.2 into 2 to the power v, 2 into 2v to the power 2v. If we assume that input xt is normalized, that is x max is equals to 1, therefore xq is equals to 3 rho is equal to power q is normalized, that is for xqnr sqnr is less than equals to 3 into 2 to the power v. Expressing the xqnr in decibels, we get the that xqnr decibel is less than or equals to 4.5 plus 6 v decibels. Thank you.